and then we'll get cracking with the presentation. So, my name's Matthew Brooke-Peat, and I'm going to talk to you about as-built thermal bridging. Just to give you a bit of an insight as to who I am and what I do. Since May of this year, I've become very recently in fact, I've become the course director for architectural technology here at Leeds Beckett University. So I'm responsible for the strategic management and delivery of BSc Honours Architectural Technology and the MSc in Architectural Technology and Design. In addition to that, I'm an active researcher as well, and I work with the Leeds Sustainability Institute and have done since 2012. So I've done a lot of forensic investigation into thermal bridging. That's one of my specialisms. Hydrothermal simulation is also one of my specialisms as well. You may have heard Nick talk about that earlier. In tandem to that, I've run a practice as well where I've been offering consultancy to designers and energy assessors and manufacturers and a whole range of other people on thermal bridging issues. So we're very much looking at the forensic side of it today. What I will kick off with is a bit of a notice, just to say that some of the slides I've stripped out annotation, so we're focusing on the sort of key attributes that relate to the thermal bridging. So just be aware of that. Just so everybody's on a level playing field here, let's just try to get a grip on what I'm talking about with thermal bridging here. So if we're looking at heat loss from a building, we've got a number of paths. We've got the plane elements, which are the walls, any openings, the floor, the roof, etc. We've got thermal bridges at junctions where these plane elements actually meet. So the corner of two walls meeting, a floor meeting a wall, wall meeting a roof, etc. We've also got air permeability, which is essentially unintended ventilation through the fabric. And in some cases, although we shouldn't because we can design these out, there may be thermal bypasses. And this is where air is circulating around insulation and bypassing it effectively. Okay. What else is it? Yeah. Okay, I think that probably covers that a little bit. There might be something else that comes to mind in a minute. If we look at the fabric heat loss and the heat transmission coefficient, which is basically this here is the amount of heat you're losing through a building in watts per Kelvin. It's calculated by taking your plane elements, so it's the area times the U value, and you add that together with the linear thermal bridging, which is the thermal bridging at junctions. So it's the length of each bridge times its psi value, which is the heat loss calculated for that thermal bridge, and you add the point thermal bridges, which is a summation of the number of point thermal bridges. Okay, by and large, the point thermal bridging gets ignored in energy assessments. For some reason, building regulations don't seem to be that interested in it. Okay, not quite sure why. I think it's because we're still grappling with this part, that this is sort of an additional complexity. However, where these cause excessive problems or excessive bridging, and there's a potential for moisture risk, then they should be assessed to ascertain whether they will cause that risk or not. Okay.
At the risk of being thick, what do you mean by points though?
I'm going to come on to that in a moment. Okay. So yeah. Okay. So the problem that I'm investigating from this perspective as a researcher is that the building regulations assume that the thermal bridging parameters that are claimed during the design are actually achieved by the construction. So in other words, what's being built, is that what was originally intended? Is that what's being predicted? Okay. And there's growing evidence, and you're going to see some of it as well, that suggests that this is not the case. In recent years, there's been lots of work, various academic institutions, an organisation was formed called the Zero Carbon Hub to actually bring all that together and, at the request of the government, to summarise it and sort of look what it means, what industry has to do really to respond to this. That work is collectively known as the performance gap, and this is where you get a difference in performance between what the design intent was and what's actually the as-built situation is. Okay, so from my perspective, how can you assess that with thermal bridges? because we can measure heat loss from buildings, entire buildings. We can use co-heating tests where we can measure the amount of energy we have to input to sustain a certain condition, and we can do that, and we can measure what's known as apparent U values using heat flux plates and so on. Thermal bridging is quite difficult to actually measure. It can be measured, but it's quite difficult to measure. We can measure air permeability and all those kind of things as well. So if you measure the heat loss from an entire building and you measure all the component parts as well, and you subtract that, what you should be left with is a thermal bridging. But then how do you look at the individual thermal bridges? And that's what we're doing here. So just to explain the different types of thermal bridges, if you've got a timber frame structure, and we've got some timber eye studs here, very basic representation of one, and you've got repeating thermal bridges, which are the studs that are occurring in this case at 600 mil centres, okay, because that's what the structural design demanded. Where you come to the junction, you've got what's known as a non-repeating bridge, and that's the connection of those two walls. So when we're looking at repeating thermal bridges, we generally take account of these in U value calculations, and what I'm talking about here is wall ties that are penetrating insulation. We could be talking about mortar joints in the blockwork. They're repeating thermal bridges because they repeat at regular intervals, okay? Yes, you may get clustering of these things at junctions, and that's where we may look at it actually in the non-repeating thermal bridging. Another example of repeating thermal bridging, lightweight steel frame structure. So you've got a steel stud, plasterboard on the inside, sheathing board, insulation on the outside of the sheathing, and then you've got a cladding bracket going through the insulation that's fixed back to that stud through the sheathing even. So there's two bridges going on there, one through the primary insulation layer, which is the cladding bracket, which is obviously at regular intervals, and then there's also another one here, but it's not in the primary insulation layer, so it's not that much of an issue, but it's within that air void, because the air void would have a greater thermal resistance than the steel. So linear thermal bridges at junctions, you've got a wall here and another wall coming in, and this is a thermal model. What it's showing you here is the temperature of that fabric, and the grey lines are what's known as heat flow lines, and you can see they're affected as you approach the corner. And you can also see that the temperature dips in the corner as well. Okay, you'll see some of these in more detail later on. And when you actually calculate this using thermal modelling, you get what's known as the psi value. Okay, so this is the heat lost per watt. It's a watt for each metre of junction for every Kelvin of temperature difference. Okay, between internal and external environments. Okay, I was twisting my tongue a little bit trying to get around that there. So a point thermal bridge is, well, this is an example of one here. You've got a concrete floor slab, you've got a structural steel column, that's going through the floor slab, and it will be founded probably on a pad, and then you've got composite cladding which is fixed to that steel column. Again, calculate this using thermal modelling. Gets what's known as a chi value. It's spelled CHI, looks like a little cross. Okay, and you can see what's happening here. There's a reduction in surface temperature around that column because steel's very, very conductive, and heat will take the path of least resistance. Okay, so that's what we mean by point thermal bridge. And these thermal bridges are caused by a number of scenarios. So first of all, you've got geometric thermal bridges. So we're looking in plan at a sort of a fairly bog standard cavity wall here. Blockwork, partial fill cavity insulation, brickwork, external leaf. Okay, we've got continuity of insulation here, as you go around the corner. And if we're taking our heat loss through the plane elements here, okay, we've got this extra bit of material at the corner, and essentially that's the thermal bridge. And the reason you're getting that because the internal surface and the external surfaces are different sizes, and because of that you get essentially additional heat loss in this corner even where you've got continuity of insulation. Okay, so you could have this in many different scenarios. You could have it an exposed floor, say above a porch, maybe if the first floor projects out or so on. So there's loads of different scenarios this could apply. When we look at the temperature distribution, you can see here at the edges of the model, the heat flow lines are perpendicular to the surface, which means it's going straight through. And this is a metre cut-off from the corner in this model. Okay, and as soon as you start going towards the junction, you can see that they're starting to bend and be affected by the junction. So even that far from the junction, it's been influenced. Heat flow has been influenced by the junction itself. Okay. And you can see that in the temperature profile as well. These models, by the way, there was a quote used earlier actually from Colin King of the BRE. He's actually got that from somewhere else, believe it or not, about all models are wrong and some are useful. It's how wrong do they have to be for them to be useful. This is actually a relatively robust modelling tool. Actually, is thermal modelling. It's actually a type of numerical modelling. It was originally developed in the 1950s, actually, or out of the mass that was developed in the 1950s for aircraft design. It's been used a lot in structures, and it's been used a lot in heat flow analysis. The type of software I've been using is Trisco, published by Physibel, and that's a package which is specifically used for building modelling. Okay, so however, models are still simplified representations of the very complex world, so we do just need to bear that in mind. Another example of a cause of thermal bridging is what's known as a constructional thermal bridge. So here you've got the same masonry wall type, and this is a gable end. We're looking as a section detail here. We've got a roof which is timber trussed rafters, and then it's insulated between the rafters, and then over the top of the bottom chord. And what we've got here, you've got your plane elements, which is the wall, and you've got the roof, well, the ceiling, which is the plane elements. And because the block work is essentially going straight through where the insulation should be wrapping around, obviously it can't for structural reasons, that is the thermal bridge, and that's a constructional thermal bridge. And again, if we look at that as a thermal model, you can see what's happening. Where you get this narrowing of the heat flow lines as well, that means there's more heat going through there. Okay, so it's not just the psi value we're interested in. We're interested in these temperature distributions as well, because they tell us a lot about the thermal detailing quality of a junction. Okay, and as designers and so on, you'll be interested in that, I assume. So generally, when we're calculating these things, we build a thermal model. So this is this normal corner arrangement in plan. Okay, and this is the equation for it. And essentially the L2D part comes from the model, because this is the heat flow. We can calculate the L2D, and then we're subtracting the effect of the plane elements, and what we're left with should be the thermal bridge. Okay, so that's really the quantification of a thermal bridge. So you start out with the whole junction, you subtract the plane elements, and what you're left with is a thermal bridge, in essence. Okay. There's a number of different ways of measuring heat loss. You can either use internal heat loss area, which we do under the building regulations. So all energy assessments for building regulations purposes will use the internal heat loss area. If you're familiar with Passive House, they use the external heat loss area, and that's also a common approach in Europe, as in continental Europe, that is. So the German standard, etc., use that. The physical reality here, though, is that if this was the same building and you were measuring the heat loss, the actual amount of heat going out of the building would be the same. It's just the accounting procedure that's different. So yes, you would get a different value in terms of where you're using your U values and you're timesing them by the area. The areas are different, so you're going to get a different value. But then when you factor in the thermal bridging, essentially you should arrive at the same amount of heat coming out of the building. Okay, but what this does is it overcompensates for the U values, so you tend to subtract the bridging, whereas here you're adding the bridging more often than not. Okay, there are cases where it might not be the case like that, but generally that's what happens.
Would you advocate one over the other? Does the external seem more robust to you?
If it's done properly, you should end up with the same, really. So I'm not that bothered about it. but I tend to work primarily with internally because I'm working obviously either from a consultancy point of view with the building regs, and it's also what people understand that I'm talking to by and large. However, quite often I also work with the external as well, because if I'm working on passive house projects I have to give them the external stuff anyway. Certain context. Yes, it's a good idea to over-engineer everything and go down that route in terms of overcompensating, and then you've got a factor of safety in there where you're bridging. The thing that passive house does is you only really calculate thermal bridges if you're reducing the insulation by more than a third, basically, of what you've got elsewhere in the walls or roof or whatever, is connecting at that junction. Okay. So in that respect, that's where you may end up with different heat loss values, and it would be overcompensating on the U value side of things there. Okay, so yes, it's good practice to do that if you can do it, but I'd rather assess everything so I know where we're at really. So the other important thing about thermal bridging is the temperature that you're going to create, the surface temperature that's going to be created at the junction. We assess it on what's known as the temperature factor, FRSI, and it's in the building regs as a minimum that you must achieve in some scenarios. This is known as a critical temperature factor. We calculate it based on the internal surface temperature that's generated in the model and the internal and external air temperatures that we specify in that model, and we do that by standard. Now the beauty about this calculation is you can get all of those parameters by measurement as well. You can get them from thermography, and you can get them from just thermometers basically, and surface temperature, thermocouples and the like. However, this temperature factor is actually based on the resistance of the construction. It's not the conditions that are important here, it's the construction. But all this is just an alternative version of a resistance calculation. Okay, so it is the fabric of the building that's important more than the conditions for calculating this temperature factor. Okay, so there's a third party document to the building regulations, which is BR-IP 106. It's published by the BRE, and as you can see here, if you're in a dwelling and you want to avoid mould growth, you've got to have a temperature factor equal to or greater than 0.75. If you've got a swimming pool, it goes up to 0.9, and this is to avoid mould growth. Mould will occur at around 80% RH at the surface and above. Okay, surface condensation will only occur at 100% RH. Okay, so this is why the values would be different, and obviously in different buildings you've got different risks going on as well. So for example, storage buildings, not many people, relatively low moisture load. You can see we're not that worried about surface condensation, but when you get to swimming pools, breweries and laundries and so on, okay, surface condensation is much more of an issue because you've got a very high moisture load. Okay, so hopefully that's probably setting the whole thing in context there. Moving on to what we've actually done with the research here. So these have been done on live projects. So there were live projects at the time the modelling was done and the site investigation was done. So the first thing I did is I reviewed the design information for some projects, okay, and then I thermally modelled the junctions for those projects, and I've got some base values then. So I'm expecting this is how things are going to perform. Then gone out onto site, made some site observations, undertaken some measured surveys, and actually established what has been built. Maintained a photographic record as well, so I can refer back to that. I've then thermally modelled the as-built junctions where I've found a difference, okay, between the design intent and what I'm actually presented with on site. Then undertaken a comparative analysis, because it's a research project after all, and I've compared the design results with the as-built results. Okay, this is part of a much wider research project actually, so I've also compared it with what the designers are claiming, and I've also compared it with what the building regulations would expect you to be modelling or have values for, and actually comparing that with if you model everything that really you should be modelling. Okay, so I'm looking at various different scenarios here, but I'm just focusing here on the difference in this presentation in the as-built junctions. Okay, and obviously it's research, so I've got to report the findings, and then I've got to discuss that in a wider context. So in other words, what does it mean for industry? What can we do about it if there is a problem at all? Okay, so just an illustration of that approach. We've got a design for a junction detail. We thermally model it. We go out onto site, observe what's being built, and then we thermally model it. Okay. There was a number of site visits to see this in various different stages to ascertain what's gone on there. So a couple of interesting points to note here. First of all, this was a passive house project. In this case, we've got this masonry wall which has got 300mm of insulation in the cavity, and then this large area here was infilled with a timber frame sort of construction. And we've got a balcony detail, which is what this is. Okay, the design showed insulation in the floor, acoustic insulation in the floor here, and it was supposed to go through the webbing of these truss joists. Obviously, you can't do that with a roll of insulation because the webbing's in the way. Okay, but that's what the design showed, so that's what we modelled. Interestingly, the junctions for this, there was actually, wherever you got a balcony upstairs, you also had a set of glazed doors downstairs as well, going out onto a patio. Now, the design information didn't show that on this detail. There was a separate detail to show you the head of that junction. But because I've pieced all these bits together, I've modelled the design, so I've had to interpret the design to model it. Okay. The other thing as well, that joist wasn't quite exactly where it was shown in the design. It was actually tight against the wall, so there's a bit of difference there as well. Okay, but that's the illustration of the approach. To test the method, we ran it on some pilot studies. And sorry, I keep saying we, I'm talking about me really, it's me that's done all this. I tend to use we a lot, as in the university, legal reasons as much as anything. What we're looking at here is a windowing plan. This is just to show you the difference that window position will actually make on heat loss. So if we go to the building regulations and use the minimum 30mm overlap between the back of the window frame, which would be here, in the model it's replaced by an adiabatic boundary here, so you're not actually seeing it, but it is there in the model. It's just that we're focusing on the junction. I can explain that later if anybody's interested in the detail of that. But what we're doing is we're looking at window position. So if we've got an overlap of 30mm between the back of the window frame and the front of the cavity closer in this cavity wall construction, that's what's required by building regulations. We've calculated the psi value in this scenario, you can see that there, and we've calculated the temperature factor. If we then move the window in line with the insulation in the cavity, or the front of the window in line with the front of the insulation in the cavity, you can see it dramatically reduces the psi value. Okay, yes, there might be a need for the windows to be out there for fitting in with the local vernacular, etc. But purely on performance approach, and this is ignoring any necessity to actually have a check rebate for weatherproofing, etc. But if you're just fitting it into the opening, bring it in line, you can see dramatic reduction in heat loss and an improvement, obviously an increased internal surface temperature at that junction, which increases the temperature factor, reducing the risk of mold growth. Okay, not that it would be a problem anyway in the first instance. Okay, what happens if we take the window completely outside of the insulation layer there? Okay, you can see the heat loss goes up, the temperature factor goes down, and it fails building regulations. Now you think surely nobody in their right mind would do that. Look what I found. Right, okay, so the design of this actually did have that minimum overlap. However, late in the day, somebody said, in fact it was a conservation officer on this particular project, that these windows need to be moved out to meet the local vernacular. Now the local vernacular was solid wall properties, so you don't have the same issue here traditionally because we haven't got the insulated cavity, and that's fine, they've matched that. But what they haven't done is they haven't addressed the thermal bridging inside. Okay, so all we're seeing here is the plasterboard in the reveal stripped away. you can see there that the outer flange of that steel lintel, which is connected because it's a top hat style one, it's a combined lintel, is exposed internally. Obviously it would have plasterboard underneath it, but the point is there's excessive thermal bridging. We modelled that and you can see, yes, there's a risk of mould growth. So basically that fails building regs. However, this building is there in existence. Whilst on site, we had a look at this and we could see condensation forming on that steel. Okay, so there's a interstitial condensation risk as well in that junction, sort of around here. Okay, so they will have problems. What could you have done about that? Well, the only thing you could have done in that instance, because it was so late in the day, would be to actually line the reveal in some way with a reveal liner, whether that's insulated plasterboard or some other system, but to insulate the reveal in some way internally. That's the only way around it. There is an issue here as well, is that this is full fill cavity insulation and the cavity closers missing in that instance. It wasn't missing on all of the junctions, so quite why it was missing there I'm not quite sure. Whether somebody would try to put one in and not afterwards, again, we can't be certain. So, these things go on. This is a different project, but by the way, I modelled loads of junctions on these projects. I'm just picking out some basically to show you. What we've got here, the architectural design wanted the windows to be sat quite far back in the reveal in this instance and expose this masonry. There was also some stone properties on this site as well, which I think is where the detail originally came from. So what they've done there is they've used an insulated DPC, which is a very old style of detailing. Normally it's the other way around though, it's the blockwork that returns into reveal, but this way it's the brickwork. We have modelled it. If you look at the default values under the building regulations, it's 0.1. If you look at the accredited construction details, which some of you will be familiar with, it's 0.05. We've thermally modelled it, so it's somewhere in between, 0.064. Okay, so it's not failing building regulations, it's not a very good detail, it's acceptable, but that's the consequence of the design feature. Interestingly enough though, what you can see in this picture here is that there's a split lintel arrangement going on here. We've got a steel outer lintel and we've got another lintel inside here. They're two separate lintels. We've got partial fill cavity wall insulation here, and that's 100mm PIR in the cavity. You can see first of all it's not tight back against the inner leaf at that junction, and there's no cavity closer either. Okay, why not? So same building, looking at the eaves, what you've got here, masonry wall construction going straight up. We've got this timber cassette roofing system that was craned, pre-built, craned in kind of thing, and then you're connecting it at this point, and then it was to be infilled at the eaves with insulation, and then you've got quite a thick floor structure coming in here as well. Okay, we modelled the design, or I modelled the design. It's actually a pretty good value for eaves, is that? That assumes that that void is completely filled with insulation. This is what I found on site. Okay, this is actually a cavity barrier that they've used here, a large cavity barrier. Okay, clearly not going to fill all that void, but that's what I found. Okay, modelled that, you can see that is massively different. Okay, I had to take a typical section of the cavity barrier, obviously, because it was slightly deformed in places, and model it. So actually the side value would be completely different along that length, but for the purposes of what we're doing, I had to sort of rationalise it a little bit. Okay, massive air void there. This one is a passive house project, 300mm of insulation in timber stud. These were cassette panels, so they came to site ready built, and then they just connected the panels together, okay, using a very clever cam system. And it had sheathing board internally and externally, and then it had a second sheathing board over the top of the structural sheathing board. And it was a bit rock one which has a low conductivity. So essentially what it's doing is trying to reduce the thermal bridging through those eye studs. As a connection detail of those panels, very, very good. Very little timber here. So you're maintaining as much continuity of insulation as you possibly can, bearing in mind you do have some studs at the junction. Okay, very good. This is the as-built calculation, by the way. The design didn't show a batten. One of the battens was missing in here. So how was the plasterboard going to be fixed? This is a service void, obviously running various services in, and it was also shown as insulated as well. I'm assuming for acoustic reasons. I don't like insulating service voids to to improve the thermal performance, because it was actually the other side of the vapour barrier, because the vapour barrier in this instance was at the sheathing. Okay, I don't like putting any insulation on the warm side of the vapour barrier. And in the as-built, there was obviously no insulation here as well. So the contractor had to put a batten in the corner because he needed to fix the plasterboard something, and missed out that bit of insulation. So this is passive house, and you can see the psi value. Okay, so yes, passive houses do have issues at junctions in their design, and in this case in the build as well. Okay, but that was a design issue really, and it's relatively minor, didn't really affect the thermal bridging that much, but unless you consider buildability, how can the contractor actually achieve what you intend? So it's not all in the contractor, by the way. It may shock some of you that designs are not perfect in many instances. Okay, and I found a lot of that. I found missing drawings, we'll come on to that in a bit actually, in terms of some details, or some junctions didn't have any detailed drawings for them. We found buildability issues. This is a relatively minor one. I found others. The methodology seemed appropriate. Rolled it out onto a couple of case studies. Okay, so this one here is a passive house development of 40 some dwellings in the north of England. I'm not going to tell you where it is because I'm going to protect the parties involved. And it's a 2-storey, 2-bedroomed, semi-detached property. Okay, it was actually on the end of a terrace was this one, but it's just a semi-detached because it's the end of a terrace. This one is 500 and some homes, also in the north of England. Traditional masonry construction, but with an enhanced specification. So 100mm PIR in the floor, in the walls. It uses a composite flooring system where it's beam and block, and you've got a large amount of EPS, and then you pour concrete over the top of that, and a good amount of insulation in the roof. Just going back to the passive house, this had 250mm of insulation in the floor, 300mm of mineral wool in the walls, semi-rigid bats, and 500mm in the roof. Okay, so super insulated. It's not all doom and gloom, as you'd expect with a passive house. Some very, very good details going on here. This is a ground floor external wall junction. It's a detailed section. So this is the floor, 250mm of insulation. What they've done is, because you've got this constructional thermal bridge of this blockwork that's supporting the inner leaf. This is actually a ground bearing slab, by the way. I know it looks like a suspended slab because it's shown as being built off this blockwork, but it is actually a ground bearing slab. The reason why it's been continued into the inner leaf is to improve air tightness. That has been shown to improve air tightness as that detail. Okay, but it was designed structurally as a ground bearing slab. I think the engineer had a bit of an issue doing that, but they achieved it. What they've done with this constructional thermal bridge here is they've used low thermal conductivity blocks below ground. Here, because it was cheaper, they could use a higher conductivity block. Didn't matter, you've got lots of insulation here, and they're using that to good effect. So there's cost saving up here, but use the low conductivity blocks where it mattered, okay, in the bridging. Lots of insulation here, lots of insulation in the wall. Okay, very good detail. That's what it looks like, by the way. You're still getting some thermal bridging. It's a fact of life, it's going to happen, but can we reduce it and can we increase surface temperatures as much as we can? That's our aim. Okay, moving on to the other case study, I'm going to sort of intersperse and mix these up. This is the floor, again it's a different approach but another very good detail. This is cavity wall construction, suspended composite floor, so beam and block floor, and you've got these EPS units which actually connect into the beam and block, so it's insulated between the beams, but that insulation also wraps round the top and bottom of the beam as well, and then they put a structural concrete topping over the top. Okay, jet floor is an example of that type of system. Okay, again, a pretty good detail, because what they've done here is on the ventilated void side, they've used the same insulation they've got in the partial filled cavity here, which may add, they've taken all the way down to the foundation level. They've used the same insulation and put it on the other side of the blockwork here as well, because that is typically where the thermal bridge would be. So what they've done is they've extended the bridging down, frustrated the heat flow path, basically, is what they've done. So again, very good detailing. Okay, so these are good designs, and actually well constructed as well, that detailing. However, there were no details for dealing with this meter box in the wall. And the energy assessment, when I looked at the SAP assessments, etc., for this, took no account of that. That's obviously got a different U value to the surrounding wall. That bit of wall's got a different U value to this bit of wall, and so on. Okay. Good example here of dealing with fitting tolerances around windows and doors. Fill this gap with insulation. Doesn't have to be expanding foam. Expanding foam's not very nice stuff. It does improve your air tightness, it does reduce the thermal bridging, but it also shrinks and debonds from the surface at some point. So it's not a long-term solution. Can you find another way of doing it? There are many insulants you could use, but you'd have to address the air tightness issue as well. Okay, but the point is, it's not just an air gap. The amount of these I've seen where it's just an air gap, that does affect your thermal bridging quite a lot. Okay, and by and large, if you've got very good walls and very good windows and don't do that, that's where you're going to get the problem. That's where you're going to get the moisture. Okay. In this case, what we've got here, these windows at first floor level go from head height all the way down to the floor level. Okay. Externally, the design intent was internally they would do the same. However, the contractor, in their wisdom, decided this wasn't a client request either. I don't believe. I think this was just the contractor decided this is what we'll do. I don't know why it would cost them more, but that's what they decided to do, is to infill the lower part of that. Yes, they did infill between the studs with insulation, but that posed a bit of a problem actually in terms of assessment, because the conventions for thermal modelling deal with normal jams where you've got a wall and then the window. What it doesn't deal with is a scenario where you've got this infill panel behind the window. So I had to devise a procedure for calculating the thermal bridging at that point. So what I'm pointing out here is that some of the conventions that we use for energy assessment, whether it be the thermal modelling or whether it be whole building modelling, have gaps, okay, in their procedures. So they need development, okay. So we're coming at this from all angles really. Lintels on this project, this was specification substitution. You can see there's no cavity closer there. That's an issue. But that lintel should have been a concrete lintel according to the design. It's actually a perforated steel box lintel instead. Interestingly enough, in this scenario, it actually improved the thermal bridging. So the contractor, for whatever reason, has changed the specification and it's actually improved the situation. But there's no cavity closer. This is a piece of structural steelwork which is supporting a canopy. Okay, you've got brickwork here. This bit's going to have timber cladding. You can see you've got the same insulation in the cavity here that you would have elsewhere, where the brickwork is the external leaf. It would have that, and then it would have timber battens, and then timber cladding over the top. Now, there's no insulation here behind this steel column, and the reason why there was no insulation there is how do you get it in? Yeah, you could get some mineral wool in there, but it'd be pretty tight getting it in and so on. And in fact, actually, in some of the junctions like this on this development, it did happen, but in this instance, it didn't. And actually, there was a lot like this. This is a buildability issue, so this is down to the design. The contractor, in this instance, has done what has been designed by and large. But what can you do with this? Can you come up with an alternative canopy design? Can you reposition this in some way? Could you put that in line with the blockwork and then use thermal braking plates at the junction as you're coming through. The column's needed, by the way, because you're creating a goalpost arrangement in this case because of the loading of the canopy. It's quite a big canopy. This is the passive house one. We've got an awful lot of timber here. This is an intermediate floor running perpendicular to the external wall. Truss joists. Is it really necessary to have joists that close together? And here we've got a timber ledger. This is the contractor's fault. It's a redundant timber ledger. At the other ends, these joists were hung off timber ledgers. They fixed one to the wall here, and it's not necessary. Okay, it was just left in. Okay, did affect the thermal bridging, but you know, it's fairly nominal. But the point is, it's just redundant work. A good example of thermal bridging design, or thermal detailing rather. Timber truss rafter roofs. For acoustic reasons, you've got dense block work at the party wall where it matters. Above the ceiling, you can go to a lightweight block, an AEC block. That is an acceptable solution acoustically. But for thermal bridging reasons, because that is a constructional thermal bridge, you want to reduce the conductivity at that point. So that's a good design, is that. You can also see these are bobtail trusses as well, which is also very good, and we'll come on to that in a moment. This is where the trusses were running in the sort of more mainstream build. They were running parallel to the party wall, and what's happened here, or it might have been a gable, I don't know which way around it was. They've been filled above the bathroom with expanding foam at that point. However, elsewhere along that junction, same wall, it wasn't infilled at all. Okay. I suspect here they've done it with expanding foam because it's above the bathroom. Elsewhere it could have easily been done with mineral wool. They've used a lot of it on this project, you can see splurging out everywhere. I don't necessarily agree with this. I think you should have used a gasket around that as an air seal. It would be much cleaner and it's longer lasting. This is the eaves on the passive house project. Bobtail truss, what that does is it gives you more room to insulate, so you can maintain a greater continuity of insulation at that junction. Okay, so that's good practice. This is the case study 2, the mainstream one. This junction had no design. There was no detailed drawing for this junction, so the contractor basically had to make it up as they were going along. First thing, they've ordered trusses that are too short, or they were longer and they've cut them too short. So either way, there's a mistake being made there. They've extended the trusses then, to carry the fascia. You can see that that's a bit of an issue. So there was no drawing, then the contractors had to cobble things together. A bit of good practice though, you can see there is insulation behind the wall plate, so they can connect the loft insulation to it. I'd like to see that a little bit longer. If it's exposed on site, it'd be a good idea if it was wrapped in plastic. There are proprietary products for doing this. I'm dealing with this junction now. I also have a patent application in on a similar product for a retrofit, by the way, where you can go in through the roof and insert it and then it expands into place and so on. And it deals with ventilation as well, with the cob roof. Bit of a plug there. Right, so we're looking at a gable on the mainstream. This should be closed off with a cavity barrier and then a cavity tray dressed over the top of it. The other issue here is that cavity insulation doesn't go above the loft insulation that went in. Okay, you need to extend it, I'd say at least a block above if you can, or at the very minimum the same height. Okay, and that's what it looks like. You can see here there's a lot of constructional thermal bridging going on. It would help, and you can see it's going predominantly this way as well. So if that insulation was at least to there or even higher, it would reduce that, and at least you'd be going to a warmer airspace, so there'd be less heat flow going that way. Oh yes, and this is where they didn't insulate here as well, so you can see there's a lot of heat going through there, very high density of heat flow lines. So what's the overall impact? It would have been very complex if I was trying to communicate all the differences between the different scenarios, but essentially when we're looking at the as-built thermal bridging, This is case study 1, the passive house. This is case study 2, the mainstream house builder, but with high energy efficient design, apparently. This is the effect of the bridging. A couple of things I would say here. This building is much larger than this one. It's still 2-storey, still 2-bedroom, but it's got a greater external envelope area, a greater heat loss area. So that does have an effect. Incidentally, both of these were not built the size that they were designed to be. Okay, and that is setting out error by the contractor, poor control on site. And we're talking by a number of meters. We're not talking a couple of millimeters. We're talking by a number of meters square here in these scenarios. So one less than the other, but still an issue. Why in the passive house scenario is that so high? Well, it's a smaller building, so the junctions have a greater effect. And also it's the weakest point as well, because the walls were very good, U values, the floors were very good, and the windows and doors, etc. were very good. So the weak spot's the junctions. Okay. Yes, there was one or two issues in some of the junctions, but by and large it was very well designed and very well constructed in general. Why the windows and doors, etc. have a greater percentage than this one is because it's passive house. It had a higher proportion of glazing on the south-facing elevation to capture solar gain and have useful heat.
Sorry, Matt, is that the proportion of the heat that's lost per element?
Yes.
No,
Sorry, this is the proportion that's lost per element in relation to the whole thing. So that's 43.5% of the whole heat loss is attributed to the openings. Yeah. Okay. So it's really an issue for passive house, and it's still a major contributor to generally high efficient buildings as well. So they're my contact details: telephone number, email address. If you've got a QR code reader, zap it. Okay. Does anybody have any questions?
Quick one.
I'll go to you first, and then I think you were probably slightly quicker with Andy.
Okay. As you increase the U values of the building fabric, does the impact of the thermal bridging become proportionally more significant?
Yes, it can. Now it depends, because it depends on how you're improving the insulation in the main plane elements. Because are you achieving the same sort of approach at the junctions as well? Is it continuous? So is the insulation going up by an equal amount in the junctions? But to answer your question, the more you improve the thermal performance of the plane elements, yes, proportionately the bridging gets worse, although the individual psi values may get better, but not at the same rate as the U values would improve. Yeah. So, in other words, the better performing the building is as a whole, the more importance you need to put on the junction design. Okay. Sorry, yeah.
What's the best way to deal with an external wall that becomes an internal wall?
An external wall that becomes in a conversion?
Yeah, so you've got like a traditional masonry cavity wall,
yeah,
and then it becomes an internal wall from your extension. Is it best just to dot and dab or insulate?
Yeah.
Like, obviously you've got an external wall doing that,
yeah,
but if you wanted it to be a nice brick feature wall in your extension, it'd be.
I don't think there's a catch-all answer for this. I think it is specific to the instance.
Into it, don't they, and make it
yeah, I mean, first of all, are you going to put cavity training as well to start with? So, are you going to have some access to the cavity that then you could put a cavity barrier in as well, because that would help with the bridging. Yes, I mean I've internally lined things in those scenarios where it's been beneficial, but I have assessed it to determine whether it was appropriate or not. What you don't want to do is start causing problems elsewhere with it. At other junctions. Okay. So yeah, so yeah, it's one option. You could use IWI to improve things there. Yeah. Depends on the amount of disruption and yeah, absolutely. Whether you can fit it in as well. Any more questions? Okay. Well, I'm around for the rest of the day anyway. if anybody wants to